This is FS2, further statistics 2 from 2020. Let's do this. So we've got some statistics here about packages from A and B. We're going to test whether the variance is the same for each or whether it's greater for one the other. So obviously H0 variance is the same, H1 variance is different. Now we're going to need to make an unbiased estimator for the variance here, or standard deviation. We can use these statistics to do it. Now we have this in the formula book, which is going to help us, except we don't really have this information. But actually, somewhere else in the formula book, we can grab something that looks a lot like this here, which is this. And we can use SXX and just put it up there. And we'll end up with our estimator, S squared, is just SXX over N minus 1. So the estimator for the A company, we can say, is just this over 7 minus 1, which is 6. And we can just do that, and we'll get this, and we'll do the same thing for B, and we'll get that there. So that's pretty useful. So those can be what we'll get there. Now, this is going to be an F test, because we're testing variances here. So we've got n minus 1 and n minus 1 here, so 6 and 9. 0.05 because it's a 5% one-tailed test. We'll look in the F table here, and we'll go 6 and then 9, and that's this value here. And then if we divide our two estimators, because that's of course what we do to compare against this value here. If we take this one, we're starting A there and then B. This is 6 is 7 minus 1 from A, and then this is 10 minus 1 from B. So it goes A, B, which means you do the A's divided by the B's for this test here. And that gives us this, and that's bigger than that, so it's in the critical region. And we'll say this is a result that means we'll reject H0. And we'll say the variance of the stuff in A is larger than the stuff in B. Throw in some context and make sure you pick up all your marks. Good, so we've got some more statistics here. Going to do another kind of thing here. So confidence interval this time for the mean weight of jam in a jar. Got a few things to do first. Now, this is the formula we're going to end up having to use for this confidence interval, because we don't know the variance of the original kind of original population. We only know, I mean, we can work out the variance of the sample, which is what we're going to use here. That's going to go in there. But we're going to need to use the t-test for when you don't know the variance of the actual population. And because n is quite small here, so we're going to use t7, which is not quite the normal distribution anyway. So, okay, well, let's first work out x bar, of course, because that's going to have to go in here. So that's going to be this divided by 8. So that's quite nice and easy to do. S, we need this formula. Again, that's not in the formula book this time. So we are going to need to know that. We can just, though, of course, once we do know it, we can just use these two statistics here to get it nice and quickly. And then we can just use our confidence interval. Sorry, no, we do need Tn minus 1, don't we? So n minus 1 is 7. It's a two-tailed because, of course, confidence intervals are always two-tailed, biggest down smallest. So we're looking at the t-tables here for 7 and then 0.025. That'll be that one there. So we're gonna we've got everything we need now. I think we've got x bar minus the t value, which is this, into root of that there over root 8, and then the same thing but with a plus here, and we'll get our interval there. Should we the average is 440? Should we be concerned? Or it states the average is 440. 440 is in the region, so we shouldn't be concerned. It's in the confidence interval, so we're 95% sure that that's fine. Good. Question 3 then is an interesting question. We've got some plots of residuals in 3 different pieces of data here, and it's asking us which is feasible. Now, this one isn't feasible here. The other 2 are, but this one isn't, because if all of the residuals are positive, then what that essentially means is it looks a bit like this, I guess. You're drawing your line of best fit in the wrong place, mate. Like, it just needs to be higher. You need to have some negative residuals where you're below the line and some that are above. So, yeah, this is just not feasible at all. Technically, I mean, the thing to say, I put it at the bottom here, the residuals must all sum to 0, and these clearly aren't going to sum to 0 because they're all positive. But these could, right? These could, and so could these. Now, okay, so these are feasible, but are they suggesting a linear or a non-linear relationship? Well, this one here, what's kind of going on here is you can draw it like this if you want to, but you've got a load of them that are under the line for a while, and then a load of them are above, and then a load of them under, and so on. And there's a pattern here, right? And it's not linear. So you probably don't want to use a linear thing here, because it's very predictable that sometimes they're over and sometimes they're under. You only really want to use linear relationships if the residuals are all scattered all over the place, where some are above and some are below, and there's no real pattern, and you just shove a line through it. Whereas if there is a pattern like this, and putting a line means that consistently you'd have patches where some are below and some are above, that just means that there's something else going on more complicated than the line. So to summarize, this one and this one are feasible, this one isn't, and this one is the only one that also should really be done with a linear regression or whatever. So yeah, good. Question number 4. So we've got, obviously this is just tossing a coin, so it's binomial tossing it n times or m times probability p. So we'll just say, I mean, the question's asking us about unbiased estimators, so maybe I should just say here, to be an unbiased estimator for a parameter theta, then the expected value of the statistic that you're using to estimate needs to also be theta. That's if it's unbiased. If it's not, then you have some bias that's just the expected value minus theta. But if they're equal to each other, then therefore your bias will end up being zero, and therefore it's unbiased. So okay, we have this kind of idea here. Now, like I was saying, we've got some binomial distributions going on here essentially, so that's cool. And yeah, what's the expected value of s? Is what we'll say. Of course, we can say that the expected value of x is np and y is mp. And expected value of s, therefore, is just, well, these two things are just numbers, so we can just, there's nothing to do there. Expected value of x plus y is just expected value of x plus expected value of y. And of course, we know those two things. They're just np and mp, so we can put those in. We can factorize out the p and then cancel, and we just get p. And so therefore, it's being used to estimate parameter p, which is theta, in this case, and E of s is p, so that's good. So this is unbiased. The two things are equal. And likewise for E of t, the half doesn't matter, obviously. The n's also don't matter. I've written this is just 1 over n x, and then 1 over n is just a constant, right? Because n is just a number. So I can just do 1 over n e to the x, and so on. And then, of course, we just have ex, ey. We know what those two things are. We put them in. There's, of course, np divided by n is just p, and np divided by n is just p. P plus p is 2p, divided by 2 is p, and so therefore they're both unbiased estimators. And then it says, prove for all values m and n that s is the better estimator. Now, to be a better estimator, you want your variance to be lower. I mean, if they're both unbiased. So we want the lower variance. So now we need to start thinking about the variance of this and this. Now, we need to use that chapter 4 idea, where if you're combining variances of like some kind of linear combination here, then this one becomes a squared out here, and this one is squared out here. And you always add, remember, even if this would have been a minus, which is not going to be here, but you would always add. So, okay, let's think about the variance of s then. I can write s, if I split it halfway down like this, I can say it's x over n plus m plus y over n plus n. And then I've just written it with the x and the y down here. Now, that's just because this is a constant and this is a constant. So this can act as my a and b, these two things, when I take the variance of s. So the variance of s, therefore, is this thing squared, so that's acting as the a, times the variance of x, and then plus this thing squared, which is acting as b, times the variance of y. Now, of course, the variance of x and variance of y, if they're binomial distributions, is just np1 minus p. I think you learned that back in regular A-level statistics, if I'm not mistaken. So we can replace those two things in there. Of course, this one uses m's instead. And yeah, we can actually factorize out p1 minus p here, which gives us this. And then this n plus m can cancel with one of these ones, and then this just goes to the top, and I think you end up with this here. So that's just a little bit of algebra there. Factorize out p into 1 minus p there, and then I put that at the top, and then you cancel one of these m plus n's with one of those, and you end up with this here, I think. So that's variance of s. I'll just shove it there. Variance of t, same idea. So this is a constant, so we're just going to square it straight away, just like these. And then you can write this as 1 over nx and 1 over my, and then you'd square those two things as well, just like you do here. So it ends up looking a bit like this. I mean, there's plenty of different ways to write it. We keep using this idea up here. This will cancel a little bit down there. We can factorize out p into 1 minus p, I think. Is that what I've done? Oh, I've combined the fractions, of course, so just times that there, times that there, and times those two together. Now I think I probably factorized out p into 1 minus p, and we end up with that there. So that's the variance of t. So we've got those two things there. And now I've already said it, for a better estimator, you want a lower variance. So if we're trying to show that s is the better estimator, we want this to be less than this. And now I think I'm being a bit cheeky doing this way around, but I think it'll be okay. P is a positive number because it's just a probability, and it's less than 1. So this is a positive number, and so is this. So I think I'm okay to just cancel those down without worrying about this sign or this inequality here. So maybe just make a note of why you can do that. I've obviously said it out loud. Here we can just times by 4 times by n plus n. Again, all of these things are positive, so I don't need to worry about changing the sign at all. We end up with this here if I just times across and do a bit of stuff here. If we expand that out, we get this. We can take that away, we get this. We can then refactorize that to get that. And now this is always true, this last statement I've got to. But really importantly, everything that I've done, if you read upwards, is reversible. Like every single step that I've made is completely fine to do backwards. So I can say, and you might want to write it all out again the right way around, but if you start here and just work upwards, you'll get to here, which is what you wanted to show. right? By the way, this is always true because m and m are two different numbers said in the original question. So yeah, that's all good to go. So I think we're done, and I think that's the whole thing. That's question 4 done. Question 5 is about probability density functions. So okay, here we have this function here. Show k is this. Now, of course, for a probability density function, the area underneath it is 1. So we can just integrate this function between 2 pi and 0, and that will be equal to 1. And of course, this will lead us to finding out what k is. Of course, expand out the k and then integrate. Cos integrates to sine. We're going to put some numbers in. This mostly goes away, and you end up with k as 1 over 2 pi. Good. So that was nice and straightforward. We've got a random variable y, which is normally distributed, and e of y equals e of x. Now, just note e of y is just mu, is mu here, because that's what that does. That's the mean. That's the expected value of y just there. Expected value of x is just pi because of the symmetry within this curve here. And clearly this is a symmetrical thing because 1 minus cos of x is symmetrical, so 1 minus cos is. So e of x is just pi. Now you could do some calculus to prove that, but it's only 3 marks here, so I think we're good to assume that we can just state symmetry makes e of x pi. Now, of course, I've already said e of y is mu, which means mu is equal to pi, and that means when we get down to here, we can just say we're answering the question g of pi equals f of pi. So let's put in pi into g. Now, if we do that, this becomes a pi, and that becomes a pi, and that all becomes a 0. So we just end up with this e to the power 0, which is just 1, and we just end up with this here. Now, when we think about f of pi, that's in this range, so we just do k, which is 1 over 2 pi, times 1 minus cos of pi. So we have this, and I think we can solve this for sigma. Obviously, this goes away, as I've said. Cos of pi is minus what is it? Cos of pi minus 1, right? So we get 1 minus 1 is 2, and that cancels with that 2. And then we can kind of multiply this pi over the top, which will cancel with the root pi down here, just to make a root pi on top. And then the root 2 can stay here, and the sigma can multiply over there. And I think we end up with this answer here. Calculate the error in using this as an approximation to that. So all we need to do here is work out the probability of this and the probability of that, and then find the difference. So it doesn't really matter which one we do first. I thought I would do this one first because this is fairly easy to do when you know mu is pi, which we already said, and sigma squared. Well, sigma we worked out was root pi over root 2, so sigma squared is just pi over 2, right? And so we can put this in a calculator. You can just do cumulative normal distribution with mu this, sigma root of this, and lower this, upper this, and you'll end up with this probability here. And then we can think about this one here, but of course to do that, we just need to go back up here and just integrate this function, with k as this, of course, between pi over 2 and 3 pi over 2. So that's how we find the probability of that. So just integrate between those two bounds. We get this, do some integration here. Obviously, I think I just took the 1 over 2 pi out, and then integrate that to an x, integrate that to a sine. You can, just for the hell of it, because you want to, you can do some exact values here and try and do this without a calculator. Sine of 3 pi over 2 is minus 1 because it's up and then down, and then it's the bottom peak 3/4 of the way through the period. So that's minus 1, and then of course pi over 2, and then sine of pi over 2 is it's just a regular old 1, so that just goes there. Then this sorts out itself quite quickly, and you do some stuff, and you get this as your answer. And yeah, that's question 5 done, I think. Oh, which is this is a decimal, I guess. Sorry, it's not done, is it? Because that's the approximated value. That's the real one. So it's going to be this minus this for our difference, and that's the error just there. So yeah, apologies for not remembering to do that right at the very end. But yeah, cool. A new employee, Kim, joins an existing company, which I'm not going to try and pronounce from fear of being demonetized. And she does a bunch of stuff, and she's got a confidence interval with a sample of 25. And apparently this confidence interval is a bit wider than it usually should be. And so she's worried that the variance of the things being made has changed because this is a bit wider than it usually is. So we're going to test at a 10% significance level whether or not it has done. So okay, state hypothesis. Clearly, we may as well do that first. H0 is that the variance is still just this. Sorry, the standard deviation, of course, is still just this. And H1 is that it's not. So cool, we start there. Next, what we can do is we can use this confidence interval here to find mu, because we can just add them up and divide by 2. Mu, or x bar, I should really say, is going to be in the middle. So that's going to be our x bar. And for the second time in this video here, we're going to use this same formula here for our confidence interval, except we're going to do it backwards this time, because we have the interval and we have x bar, and we can look up the t-value for 25 minus 1 at a 95% level, and we can use all this. We have n is obviously 25. We can use all this to find s. So okay, let's look in the t tables here. T24, it's just 1 minus that of this, because of course it's a two-tailed test, lower and upper, so half of 5 is 0.025. Look in the tables for 24, it's all the way down here. And now we can set up, and it doesn't matter which one, whether you do this or this equal to this or this, it doesn't really matter. I think I went for the lower end if I remember correctly. 1.193 is equal to x bar minus the t-value we just looked up into s over root 25. And we can solve this for s, of course, take away that from both sides, divide by this, times by root 25, which is just 5. And we end up with this value here. So that's our s value, and that's really helpful to get because, of course, we can now test this against the standard deviation that we think it should be according to the H0. So okay, next we need to think about, so we've done that now, we need to move on to our different test here, which is that we can use this. This is in the formula book, which is really helpful, but we can say that the sample standard deviation here, when you divide by the true variance down here, well, this is the sample variance, isn't it, s squared, times n minus 1, that's what is distributed via a chi-squared distribution. So, and that's the distribution that we're therefore going to use in our 10% level test. So, okay, we've got 24 is just obviously n minus 1. We've got our value that we found via all this stuff in here, and then we've got the variance given to us by H0 up here, down here, sorry, I should say. And then we've got chi-squared of 24. So we look in the chi-squared tables, I guess. I mean, first I could just do this division here to get this. And then we can look in the chi-squared tables, which are quite a large table over here. We've got V is 24, and we're looking, I mean, it's a two-tailed, right, at 10%. So we're looking for 0.95 as our top end and 0.05 down here as our bottom end. So that would be this and that. And we can see here that our value here sits comfortably within this range, and therefore there's no evidence to reject H0. It's not in the critical region, it's in between the two values we have there. So we're not going to reject H0, we're going to say that standard deviation is still 0.175. And then it says find the 95% confidence interval for the mean length of the rods. Well, now that we know the standard deviation is 0.175, we can just use the first formula you learned for confidence intervals because we're assuming this is the correct standard deviation now. So we can just use this in here. And Z actually, you can actually just remember that Z value is 1.96 if you want to. We're now doing a normal distribution thing. But otherwise, just look in the normal distribution table, and you see for probability of, well, again, it's two-tailed, isn't it? So probability of 0.025, we get 1.96, this one here. And so that's what we'll use as our Z value, and then we'll use these X bars that we got from the sample, and yeah, then we'll use our standard deviation that we and now know to be correct based on this test that we did before. And root n is still just root 25, and we end up with the interval of this as our confidence interval for the mean length of the rods. And yeah, we end up with this paper. I think this paper had two quite interesting questions towards the end. Question number 7 then, fence polynomials come in two sizes, large and small. The large have mean this, standard deviation 5, so that's variance 5 squared, normally distributed. Likewise for the small, we just have this and this squared. And now we're going to take a sample of 3 large. So firstly, we need to make a distribution of taking 3 large as a sample. So we'll call that x, and we'll just say L1 plus L2 plus L3. And now the expected value of x is going to be just 3 lots of the expected value of L, so 3 lots of that. And the variance of x is, again, just going to be 3 times the variance of each L, which is 5 squared is 25, so 3 lots of that is just 75. You don't square the variance because we're not timesing any of these panels by anything. We're just adding together a few different panels, and that's when you just add together the variances. We'll get to a case later where we do square, and I'll try and be a bit more clear about the difference there as well. Anyway, now we make another sample of y, we'll call it, where we add together 8 smalls. Of course, the expected value of y is just 8 times 74, and the variance of y is just 8 times 3 squared, which is 72. And now let's make one more distribution z, which we'll call x minus y. The reason I've done all this is because x is a distribution that describes 3 large, and y is a distribution that describes 8 small. And so if I do x minus y, I want x minus y to be positive. I want the value of x to be bigger than the value of y, because that means the 3 large panels will be bigger than the 8 small. So let's make another distribution, and let's look for the probability of that distribution being greater than 0. Because if x was greater than y, then this would be greater than 0. But okay, what's the expected value of this distribution here? Well, it's just going to be expected value of x minus expected value of y, so that's going to be 2. And the variance is going to be, just be careful here, always add the variances. So it's going to be this one plus this one. Always add them up. So we get this here. And now we can just say Z is a normal distribution with this is the mean, this is the variance. Probability of Z being greater than 0 is the same as 1 minus probability of being less. And of course, you can just type in a calculator using mean this. Standard deviation is, of course, root this. And then you can just go upper limit is 0, and you get this number, which will be this when you do 1 minus, and you'll get the answer. Good. Now, next is when we have to change our tactics slightly. We're taking one large panel and one small one, but we're timesing this small one by a number. So let's go straight into a distribution that does that. Let's call it y. Really, you should be calling all your distributions different letters, but I was just doing a lot of copying and pasting and couldn't be bothered to change things. So, okay, we have y as this, L minus 8/3 s, because we've got one large, and we want it to be more than 8/3 times the length of the small. So we'll set up this, and again, we'll do the same thing where we look for probability of y to be greater than 0. However, we of course need the expected value of y and the variance of y to do that. The expected value is just the expected value of this minus 8/3 the expected value of this. So this minus 8/3 times that, which is this. The variance of y, now that you're actually timesing one of your, just one panel by a constant here, that's when the variance squares. And of course, always adds up even if you're taking away. So it's just going to be the variance of L, which is 5 squared, 25, plus 8 squared over 3 squared, times the variance of S, which is 3 squared. The 3 squareds will cancel actually, and you just end up with this as our variance. And so therefore, y is normally distributed with 2/3 and then 89 as the variance. And we can just go into a calculator, and we can say probability of y being greater than 0, which is to say this being bigger than that, is of course just 1 minus probability of being less. We can put this in calculator. Remember to do root of 89 as your standard deviation, and you'll get your answer as well. Next, we need 1,000 centimeters of fencing. And essentially, she can either buy 5 large, and if they end up being a tiny bit too small, because of course, the variance, then she'll buy another small panel. Or maybe she should just buy 14 small panels and be done with it. And it's asking us which one is better. Now, buying 14 small panels just for a free mark in a further maths exam is just 14 times 30, which is this. So that's going to be our number that we'll compare to. Of course, the other answer is a little bit more difficult to get, but what we need to think about is what's the probability if we take 5 large panels, what's the probability that they're going to be less than 1,000? So we set up a distribution where we take 5 large panels, we look for the expected value, which is just 5 lots of this mean here, and then we have the variance, which is just 5 lots of this, which is 125. And so x is a normal distribution with this and this, and then we can look for the probability to be less than 1,000. You can just type that straight into the calculator. Remember to use root 125 as your standard deviation. You get this. And so roughly 0.8 of the time, she's going to have to buy another panel, another small panel. So the maths will look like this. It will look like 0.8 at the time. She's going to have to buy her 5 large panels, and then an extra small one. And then 0.18 of the time, like 1 minus this, she's just going to have to buy her 8 large panels and not any small ones. We just type this into calculator, and we get this as our expected value, which is of course bigger than this. So she should just cut all this complicated stuff out, and she should just be buying 14 small panels, and that's all we need to do. 8 then is the best question on here because it's some proper maths. We've got a rectangular distribution. That's the same as just saying a uniform distribution, and between 0 and pi. And we want to be greater than 10. Now, of course, we know the area of a circle is pi r squared, so we can just say 10 needs to be less than pi r squared. We want the area to be bigger than 10. Solve this for r. We don't need to worry about positive, negative r's here, do we? Because it's just a radius. We get this. So we want r to be bigger than that. Now, this is a uniform distribution between 0 and pi. So it looks like this between 0 and pi. It's just flat between 0 and pi here. We have a value here of 1.7. Now, 1.7 is a bit bigger than pi over 2, so it's slightly over to the left here. And to work out, and what this is asking me is the probability, essentially, what's the probability of being bigger than this value here? So what's the probability of being in here somewhere? And to do that, we can just do pi minus this over pi, which is the entire thing. And we get this number here, and that's the probability of being in this space there. Cool, so that's the answer to this first bit. State with a reason whether or not the median is bigger or less than 10. Now, there's a couple of ways you can do this, but what I just thought immediately was that the median is pi over 2, because that's halfway along this distribution. Pi over 2 is just halfway here. And of course, if you use r as pi over 2 in this formula here, you end up with an area that's less than 10. And so therefore, the median area, which is 7.75, is less than 10. You can do it much more directly by just looking at this and saying, because 10 was over 0.5 of the way, less than half the stuff is above 10. And so therefore 10 is bigger than the median. and therefore the median is less than 10, but sure. Now we get some proper integration to do at the end here, which is nice. So we have a circle, OAB, with radius x, and the angle here is also x in radians. So that's kind of cool. The area of the circle is, of course, a half times x times sine of x. So that's good to go. We've got that there as well. And now look in the formula book for stuff about contiguous distributions. And you see this interesting thing all the way down here. What we've got here is we're looking for the expected value of a function of x, which is going to be this one all the way down here. Expected value of a function of x, where this here is the function, g of x. Now, what am I doing up here? Well, the f of x is the thing that's got the probability density function that you know. That's the f. So the f is this original function we were looking at up here, which this is being sort of made from with these x's here. So, okay, well, this is, the area of this needs to be 1, right? And so therefore this needs to be 1 over pi, because 1 over pi times pi is 1. And so this is just the line across f of x equals 1 over pi. So that's the function that we've got between 0 and pi. And so that's the function that will go in here. And the g of x is the function that I've named here. And so the expected value of g of x is the integral of this times that. And that's what we'll have. So it's just the integral between 0 and pi, of course, the limits of the original thing, of this one times 1 over pi, of course, dx at the end. Now, the 1 over pi and the 1 over 2 can come out of the integral, and now we just have this to do here, and that will be the entire end of this paper, is just doing this. Now, some people will do integration by parts differently. I'll just pick one of the two things, and I'll integrate it a couple of times. So sine differentiates integrates to minus cos, and then what I'll do is I'll just leave this one alone and put it over here, and then I'll differentiate it and put it over here, and then I'll put a minus integral sign in the middle. That's literally how I write it down by hand. I know lots of people do, well, almost everyone does something else, but that's how I do it. It works. And yeah, we'll just multiply these things out, I guess, to get this. This 2 can come out, the minuses cancel. And now we can just do the same thing again here. So integrate this by parts again. So integrate this a couple of times, cos integrates straight to sine. Leave that one alone just to become an x, and then differentiate to go away, minus the integral in the middle. And we get this. And then finally we can tidy that up and we'll get this. Now notice I've completely ignored this 1 over 2 pi and this pi and 0 limits here. All I've done is I've just done the integral, the indefinite integral of this, and that's just that there. So now what I can do is I can put that in to here and evaluate between 0 and pi, and also have the 1 over 2 pi on the outside. So I think this is all here. And now we can shove these numbers in. Again, we can think about exact values if we want to. Cos of pi is -1, and sine of pi goes away. So we're going to get a positive x squared here, and a -2 over here as our first bit. And then zeros, well, cos of 0 is 1, so but then x itself becomes 0, so this goes away. So does this because of this x. And this cos of 0 is just 1, so we end up with a +2 there, which takes away because it's in the second limit. And of course, that's pi squared minus 4. Now we can just multiply this out. It asks us for the exact thing, I think, in the question. And so there's the exact value there. And I think that's the whole paper done. Thanks so much for watching, and I'll see you next time.